go, what I'd like you to do is unmute and ask the question. It just is a lot easier for me than to use the chat. I kind of look at the chat a little bit, but I'm kind of like, I have like 3 or 4 different things going on at the same time. And so it's hard for me to really pay close attention to the chat. So it's better if you just say it out loud because then I can hear it. I'm like not just using my eyes for everything, I can use other senses. So before we get started, I wanted to ask if anyone had any questions. Okay. All right. And then, so the plan for today is pretty simple. So I was going to go over the quiz and the answers from the quiz. So in addition to the quiz, going over the quiz, I'm going to just keep going with kind of Haskell basics. So there's a bunch of stuff that sort of we still have to get through just to get through the basic Haskell stuff. So that's the plan for today. The exam is out. So between now and before class on Tuesday, you need to set aside an hour and complete the exam. And then the exam, I think, is only available through section 1 of the course, but everyone should have access to section 1 of the course on Blackboard. So if you have an issue with accessing the exam, oh, this is that's the wrong quiz. Thank you. See if I can delete this actually. Saw it there for a second. Okay, let me grab that. Thank you, whoever said that. Oh, it's the correct one on my screen. But not the, I didn't send the right one. Okay, sorry. Let me grab that real quick. Oh, whoops, wrong. There we go. Okay, that looks better. So this is going to be the key. Okay, so just going back, excuse me. So the idea, for the exam, you have to set aside an hour to take the exam. So please do that prior to class on Tuesday. So like this weekend or tomorrow or on Monday or whatever. And then the last part is homework 7 is still out. And then it won't be till next week that I post a new homework assignment. Okay. Any questions? Okay, and then I guess I can't really see what folks see in terms of the quiz grades. So hopefully you saw that they were graded and that you had a score. And then I tried to provide, when there was a mistake or anything like that, I tried to provide feedback. So hopefully you also were able to see the feedback from that. But I just wanted to go through kind of the answers today, just in case people had additional questions or whatever. Okay, so this is the first question, and so what I was asking is for the symbol table. Basically, if we were sitting like right here, right after the last, or right before the return M statement. So I wanted to know what is in the symbol table at this point in the execution of the function. So like after type checking, as the function is executing right before we returned. So what's in the symbol table? And so what is in the symbol table is going to be mappings from IDs to their corresponding values. And so, and really in this case, I was just interested in what is visible to M in kind of the scope of the function itself, okay, not like the global scope. Okay, so so the first thing that's visible is S, okay, because S is passed in as a parameter. So S is visible, and S has the value, the string baz. Okay, so in the symbol table, there's going to be an entry for S, and its value is going to be that string. Okay, and then the other things that are going to be visible are M, N, and I. So M is going to be visible, N is going to be visible. N is never modified in the function, and so N is just going to be the length of S, which is 3, and then I. And so in order to know what the values of M and I are, we have to kind of execute the code. And so so I starts at 1. So we can see we're going to keep looping until I is N. So I is going to end up being 3. And then M, what's happening here is we basically get the ith letter. Actually, M starts with the very first letter. So in this case, it'd be B. And then we get the ith letter, or the letter at index I. And we basically compare that to M. So what we're doing here is we're going to set M to the biggest letter in the string. And so at the end, M is going to be Z. And the way we do this in OPL is the characters, there's no differentiation between a character internally and a string. So it's just the string Z. Are there any questions about this? Okay. All right, and then the last one basically is more lambda calculus stuff. And so here, what I gave was 3 definitions. So the true function and the false function, which we went over a bunch in class, and then something new, which is this if function. And so basically, the way if works is exactly how if then else works in Haskell, actually. Well, less the lambda calculus definition. So basically, what's going to happen here is that if the B argument, so the first argument to the if function, is true, then the if then else expression evaluates to E1. If the B expression evaluates to false, then the if then else expression evaluates to E2. Did somebody have a question? Okay. All right. And so, so what I asked you to do is basically to just carry out the evaluation of like a filled in if function with all three parameters, F, 3, and 4. Okay, so I'll just walk through it. So to start with, we start with the if definition. Okay, so we'll have lambda B, lambda E1, lambda E2, and then B E1, E2. So all I did was I copied the definition of if. And then I basically have like 3 arguments. So F is the first one, and then 3, and then 4. So what we're going to do an evaluation, again, when we do, apply an argument to a function, we do it from left to right. So we're gonna take the F, which is the first argument, and we're gonna treat the function with F as a function application. So effectively, F gets passed in for B. Okay, and so then the parameter part drops off, and what we end up with is lambda E1, lambda E2, and then everywhere that B occurs gets replaced by what we passed in, which is F. So it's going to be F followed by E1 followed by E2.
Jeez.
Okay, and then so we basically ate the F, and now we have 3 and 4 left. So if we do this again, we always evaluate or apply from left to right, and so we're going to now apply 3 to the function, or the function over 3. So so E1 gets bound to 3, and so we end up with E2, F, 3, E2. And now we just have 4 left. Okay, and then we do the same thing. There's only one kind of application left here, and so we're going to plug 4 in for E2. So that's going to give us F, 3, 4. Okay, and we're not done. So now we're going to replace F with its actual function. So lambda x, lambda y, y, and then we have still 3 and 4. So now we do the same thing. We're going to apply from the right. Apply from the left. And then, so 3 goes in for x. So there's really nothing that uses x. So we're going to end up with lambda y dot y of 4. And then we have one application left. So we're going to put 4 in for y, and that's just going to return 4. Y, which happens to be bound to 4. Okay, so if we think about it, if I say if false, so if we're looking back here, if false, then 3, else 4. Okay, so well, if false means we don't take the 3, we take the 4, right? So if the condition is false, we do the else part. And that's exactly what we ended up with. But what's a little bit different here is that if then else doesn't do stuff in E1, it really just evaluates to that, whatever that expression is. And the same for E2. So if this is false, the whole thing just evaluates to E2. Are there any questions about that? About what I did here with the derivation or the evaluation steps? Or any other questions?
Before you leave the quiz, can you scroll up to 1 real quick again?
Yes.
Thank you.
Yep. Any other questions? All right. So I have a blank slate. So actually, I am going to do this thing again that I did last time. Whoops, go back. How did I do that? Which is to do this split screen and try to log in. Whoa, that's not good. Try this again. Huh, okay, hold on. That's not gonna work. Did it do that last time? Nobody say anything. Okay.
Hey there, Tim and Donovan.
All right.
Just one sec.
Having such a good time, learning so many things.
Mm. Sorry, almost there. Ah. Okay, I'm not gonna do that. Forget it. I'll just use the notes today. Okay. All right. So so we're talking about Haskell, and so I'm just going to go through like more of the data types and start talking about types and so on in Haskell. So the first thing we're going to talk about are Haskell Boolean values, which are kind of like the simplest kind of values in Haskell. And so there's two Boolean values, unsurprisingly, which are true and false. And these are not equivalent like in C or C++ to 0 or non-zero or 1. Okay, so for example, in Haskell, I can, if I'm sitting at the prompt, I can say something like true and false. And what this is going to do is basically do just an and. So this will return what, do you think?
False.
Okay, good. So what's happening is true and false are like real values in Haskell. Okay, so so as another example, I could do false or true. Okay, what's that going to return?
True.
Good. Okay, what I can't do is something like true and 1. Okay, so this will actually give me an error. And the error message is very complicated. So you can try it on your own. And so in the notes, I kind of talk about try to dissect what's going on a little bit in the error message that's given. But one of the things that it's going to say, so this is going to be an error. And one of the things that it says is basically no instance for num bool. Okay, so this is a specific kind of Haskell thing, and hopefully by the end of us talking about Haskell, you'll understand what this means. But just at a high level, what it's basically saying is that, so if we look at the value 1, that's a number. So that's part of this num thing. And what it's saying is that it's expecting, because, well, really because of the operator, so this and is a function that takes 2 arguments, and both of those arguments have to be Boolean values. And so what it's trying to tell us, this is sort of like an insight into Haskell's type system. And what it's saying is that it's looking at this value 1, which is a number, but it can't convert a number into a Boolean. So it's saying I can't make bool one of these number things. Okay, so that's part of the error. And then actually it goes on and it tries to tell you how to fix that problem. So it'll say something like possible fix, and then it kind of gives you a hint of what to do. So this is something that actually used to be somewhat unique, I would say, for Haskell, in that it didn't just tell you what the error was, it tries to help you fix that error. So this is something that I've noticed recently in newer versions of like GCC and G++, is they've actually adopted similar kind of error messages where they're trying to give you a hint how to fix your problems. So I thought that was kind of interesting. Just that this is something that I always thought was somewhat unique to Haskell. Okay, so then really Boolean comparisons. Comparisons are very similar to other languages. So when I say C derivatives, I mean languages that are derived from C. So like C++ and Java and JavaScript, so on. So, so here we can do just like standard relational comparators. So we can say something like, is 1 equal to 1? Okay, what is that? Is that true or false? This is false, right? Somebody tell me, help me. Good. Okay, so that returns true. 2 less than 3, for example. Okay, what is that? True or false?
Yes.
No, it's true. Okay, close. The true value. So then you can also do something like this. So 4 greater than or equal to 3.99. Okay, this is going to be true. So it looks like we're kind of mixing types a little bit. So this is like, we can't do this in MyPL. We didn't allow this because 4 is an int and 3.99 is a float. So in this case, Haskell's kind of doing something interesting, and we'll talk about that in a little bit. So then the only kind of difference in the comparators is that instead of not equals, Haskell uses / equal. Okay, so what is this going to return?
True or false?
Yeah, which one? You can only pick one.
True.
Unless you meant true or false, because then if you meant that, then you're correct. Okay, and then there's
Jared.
no not. Okay, instead there's actually a
Yes.
function
Before
called
you
not.
code any farther, I just did some testing and it turned out
True.
like we're all good in
Okay.
terms of function
So
declaration.
not true.
Global
Okay.
value
Is that
isn't
true or
being
false?
changed. I'll show you after the lecture.
False.
Somebody.
False.
Good. Okay. So this is fairly similar to other languages. Okay. So before we go too far, we're gonna just quickly look at types in Haskell. So this is a first, just like we had a first look at functions, this is a first look at Haskell typing. And we'll talk more about this later. So the first thing, and we've already talked about this, is Haskell, like we did in MyPL, infers types for us. And then if you want to know the type of something in the interpreter, you can use the :t or the more verbose :type command. Okay, so for example, if we're in the interpreter and we want to know what is the type, I'll just write it out. What is the type of false? Any guesses? What is the type of false? Somebody tell me what the type of false is.
Boolean.
Oh no.
It's a Boolean, okay? And actually, we already saw this here. So the type is actually bool. Okay, so what Haskell is going to return is it's going to write out actually the actual sort of type declaration. So if you're going to specify that something had a type explicitly in Haskell, which you rarely, if ever, really need to do. There are some cases where you do, but it's hardly ever. If you did need to specify something had a type, what Haskell returns when you do the type command is what that type should be. So in this case, it returns the value. So it's going to write down the value, which is false. That's what we passed into this command. And then it has 2 colons. And then it gives the type. So the way you read one way to read the colons is has type. So here what we're saying is false has type bool. Okay, so the whole full thing would be false has type bool. In other words, false has is a Boolean instance of a bool. Okay, so I can do the same thing. I'll just shorten it to :t. That stands for type. If I say what's the type of true, what is it going to tell me? Who's with me? What will it tell me?
True. : bool.
Yes. So true has type bool. Good. Okay. So there are also characters in Haskell. So for example, and you do these with single quotes, just like in C or C++ or Java. So here I'm asking, what's the type of the character A? Okay. So any guesses?
Car.
So A, the character A has the type, and I just pronounce it char. That's just a personal preference. So A has type char.
It can be called car.
There are
People
also
pronounce it like car?
strings.
What?
Okay,
Tough.
so here I'm asking for the type of the string AB.
That's
Okay,
cool.
and
I didn't
strings
know
are
that.
The
double
world is
quotes.
different now.
So what do you think the
Yeah.
type of AB is? So AB has type what?
Sting.
Okay, actually somebody had a good guess, string, which is wrong,
Stringe.
sort of.
Strange.
It's actually correct in some sense, but then it's also not in some sense. I'll talk about that later. So in Haskell, strings are just lists of characters. So a string is just a list of characters. And so the string AB has the type list of char. And the way you write that down is with a square bracket and then the type. Okay, so this is, we would pronounce this list of char. Okay, so in other words, a string is just a list of characters. Okay, so here, what is the type of this expression? Somebody tell me.
Boolean.
Boolean, good. And what is Haskell gonna, how is it gonna display this, or what is it gonna display?
False colon colon bool.
False colon colon
Oh,
bool.
Leon.
Okay, no. Close, but that's not correct. What is it gonna display?
3 equals 4, then bool.
3 equals 4, colon, colon, bool. And why would it do that? Why not? It should be false, colon, colon, bool, one would think.
It'll be ball.
Okay, what's going on here? Well, let me tell you. So Haskell uses lazy evaluation. So it doesn't need to evaluate the expression to be able to tell you that this is, oh, actually, you and I said this. We don't have to evaluate the expression to be able to determine its type. That would actually really be counter to lazy evaluation at all, right? If I have to evaluate stuff just to figure out the type. So in this case, you can look at this as just type inference, really. It's just type inference. But also what's going on here is lazy evaluation. Whoop. Okay, so then now things are going to get a little bit weird, I guess. So here, I want to know what is the type of 3? Any guesses? What is 3? I kind of already said
know,
what
it's
3
just
was,
int.
but not necessarily the syntax for that. What is the type of the number 3? Any guesses?
Is int not a thing in Haskell?
Okay, it's fine. No, probably aren't going to get this anyway. So,
Int?
3
What
has
is the
this
term for
very
numbers in
weird
Haskell?
type. Okay,
I
so
don't know.
the way that this is written in Haskell is
What?
like this. And we'll talk more about this later. But for
Numpty.
now, you can kind of think of this as any number type. And here's how we get that
3 is a numpty.
from what's printed here. So what this is saying is that T is a lowercase here, and this is a stand-in basically for a type variable. If you think about templates or generics in Java, then when you define a class that's a templated class, you specify a type parameter. And so this little t is actually basically just the same thing. It's a type parameter. And what that means is that the variable t ranges over types. And this expression num t is basically saying that t has to be an instance of a num type, or a num type class is what's called in Haskell. So basically it's just saying t is a number type. That's what this left-hand side is. So what this is saying is that if t is a number type, then the type of 3 is type t. So 3 can basically be any type as long as it's a number type. So that would include integer as a possible number type. Okay, but there's other number types. Okay, so here's another example. The type of the number 3.14. So here it's going to tell us that 3.14 has this other very generic type, which is fractional. So as long as, so 3.14 can be of any type, t, as long as t is a fractional type. So 3.14 has the type t such that t is a fractional type. And fractional is basically kind of like a hierarchy of a root class of a hierarchy of types, of type classes that represent all of the non-integer types. So basically what this is saying is 3.14 is any number type that's not one of the int number types. Okay, again, we'll talk more about this stuff later. Any questions actually about this before moving on? So this is kind of a cool thing in Haskell, in the interpreter. It's very easy, given some kind of an expression or given a value, to just determine what the type of that value is.
So what are some fractional types other than floating point numbers?
There are some types, well, there's like double and float. I think there's some imaginary number representations. I don't know all of them off the top of my head. There are a lot of underlying data types. There's a lot of types supported in Haskell, like in C or something like that. The two main ones are going to be float and double. And really, for a value like 3.14, typically this is just going to be represented as a double precision floating point number. Okay, so I just want, like I said, this is just kind of a brief intro, kind of a first look at types. We're going to move on and talk about another topic, which are lists in Haskell. And I think we'll spend probably the rest of the time today just kind of sitting and looking at lists. Okay, so we'll spend quite a bit of time with lists here. Lists are like a built-in data structure that get used a lot. And so a number of the things that we're going to do in class are going to take advantage of lists. Okay, so in Haskell, I kind of already mentioned this a little bit, but lists look like this. So if I'm in the interpreter, I can write a list like this. It's kind of like, if you've ever used Python, it's similar to Python. Okay, so basically it's square bracket and a comma separated list of values. So there's a couple things that are unique or useful to know with respect to lists in Haskell. So of course, not so surprising, lists can be of any length. Okay, and then the empty list is just bracket bracket. Let me do this. Okay, so a list of size 0 is just bracket bracket. So the other thing about lists in Haskell is that all the values in a list have to be of the same type. And in programming language land, this is what's called a homogeneous list, as opposed to a heterogeneous list. So a homogeneous, when we say a list or homogeneous, what we mean is that similar to C, you have to specify the type. Well, in C, you have to specify the type of the values that are going to go in the list. And one of the reasons for that is so that the right amount of memory can be allocated for that list in memory. So in Haskell, it's a little bit different. It's more of kind of a semantic constraint that lists have a very specific type. And so all of the values in the list have to conform to the same type, as opposed to being able to create a list that's like mix and match of values of different types. Okay, so a homogeneous list, all the values have to be of the same type. In a heterogeneous list, all the values can be different. Okay, so let me just give you an example of a bad list. So for example, if I said 1, 2, false. So again, we know 1 and 2, those are numbers. And then false, that's a Boolean. And from before, we know that we can't treat like a number as a Boolean, and we can't treat a Boolean as a number. And so this would generate an error. And it's going to be actually very similar to the error we saw before. It's going to say no instance for num bool. And what this is saying is that bool is not a number type. Okay, however, so let me take out my red pen. Basically, this you cannot do. Okay, however, numbers are a little bit more flexible. So for example, this is perfectly legal. Even though it looks like a heterogeneous list, really the way Haskell treats this is as two numbers. So it's the number 1 and the number 5.0. And if I were to type this into the interpreter, what it's going to spit back is 1.0, 5.0. So in other words, in order to get this to be a homogeneous list, Haskell basically has to treat this 1 as having the same as having like a double type or a fractional type. Okay, so that's why it writes it as 1.0. So it looks a little bit like it's promoting 1 to a, it's coercing 1 into a double or a floating point value. Actually, that's not really what's going on here. Because we didn't say what the type of 1 is, all we're really saying is it's a number. And so it's Haskell is going to pick the type or the set of types that make these two types align. And so in that case, in order to do that, this has to be a fractional type. Okay. If I wanted to mess this up and make it try to make it a heterogeneous list, and then Haskell's going to complain about it, I could explicitly give the types of the values. So for example, I could say 1 has the type integer, and 5.0 has the type double. In fact, I don't even think I need to do the second part, but if I did, it makes it more explicit that this is a problem. And so in this case, this will lead, I believe this will lead to an error. So here I'm explicitly saying 1 has the type integer and 5 has the type double. And now I have a homogeneous list. So again, that would be bad because it leads to an error. Okay. So if I go back, again, just if we think about lists, so what I did earlier was I said something like, what's the type of a character? Okay, so what is the type of H? Somebody tell me. Who remembers? So anybody, please.
Char.
Good. Char. Okay, and then I said, oh, we also have strings. So for example, the string hi. So what is, if you remember just from a few minutes ago, what's the type of the string hi?
List of chars.
It's a list of char. Good. List of char. Okay. So what about this? What is the type of that? What on earth is that?
A list of chars.
A list of char.
All right.
This is a list of char. And so hopefully now, actually this is good, because if we think about this type, list of char, you can now, maybe if you put this together with this notion that lists are homogeneous, it makes more sense why this is the type of a list. Because what we know about lists is that because they're homogeneous, every value in the list has to have the same type. Okay? So it's enough, it is sufficient to specify the list type as the brackets with the type, with one type name in it, because lists are homogeneous. Okay, so this is sufficient as our syntax for types of lists. It's actually quite nice how this works out. Okay, and then kind of just to prove or to show that a string and a list of characters are the same thing, if you were to write that in Haskell, this is going to return true. So these are really actually the same exact thing. The double quotes are just extra syntax for writing out a list of characters, which that would be annoying if we had to do that all the time. So the string notation is quite nice, but really under the hood, it's really just a list of characters. So one of the cool things is that when we're working with lists in Haskell, we actually don't have to give the type of the list, and we don't have to give the size of the list. Right? We don't have to specify either of those things. But the lists themselves have both of those. They have a length and they have a type, right? We just don't have to specify it. So like in C or C++ or even Java, you really have to like kind of give both of those things. You have to be very explicit about what the types are. In Haskell, you never have to do that. Okay, so just as an example, I can say something like in the interpreter using this let command, I can say something like my list is bound to the list 1, 2, 3, 4, and then I can say what's the type of my list, and it's going to tell me that in this case my list has. Are there any guesses what the type of my list is?
TT, I would
List of
imagine.
nums.
It's a list of nums, right? Okay, and the way that we write this is that actually the type is a list of T such that T is a num type. So that's actually the type of the list. So it's like the most generic type possible, but it does completely figure out what the most generic type is. So the type here is actually list of T with the constraint that T has to be a number type. Are there any questions? So far, pretty straightforward. So I'm going to start talking about a few of kind of the built-in operations on lists that are part of Haskell. So there's some functions that we can basically use to help manipulate, build, and work with lists. So there's a few of these. So the first one is list concatenation. So concatenating lists means you take two lists and you basically create a new list that the first half is the first operand and the second half is the second operand of the operation. Okay, so again, in Haskell, we're always returning new lists. So the result of concatenation is going to be a brand new list. And then basically all the values in the second list get sort of appended to the values in the first list in this new list. So I'm not going to write that, I'll just show you. So if I have a list 3, 1, 3, okay, and then I'm going to concatenate that with another list 3 and 7. What Haskell's going to do is it's going to create a new list that's going to be this of size 1, 2, 3, 4, 5. So the first 3 elements are going to be that, and the second and the last 2 elements are going to be that. Okay, so that's the result. What about for this one? What's the result going to be? Somebody tell me.
True, false, false.
True, false, false. Good. Okay, what about that? So what happens when I concatenate an empty list? To an
Just
empty
true.
list? Or with, yep,
Just
it's
a list
just,
with true.
just true. Okay, any questions about concatenation? So I expect you to memorize concatenation. Actually, here's one more example. What is going to happen if I do this? Is this
Error.
going to
Error.
create a new list, or will it be an error?
Error.
Good. So this is going to be an error.
Error.
Is this a
Error.
runtime error or a type checking error?
That's gonna be a oh shit actually. Probably type checking.
Type.
This is a type checking error. So the definition of concatenation is going to require that the left operand and the right operand have the same type. Otherwise, it can't create the list. And so in this case, this is a list of numbers, and this is a list of bools. Those types don't match, and so this is going to be a type error. Okay. Now, the most important list operations. List construction, which is just a colon, and usually people just call this cons. And so the basic idea of list construction or cons is that you give it a value, and then you give it a list of values, and the value gets prepended onto the list of values as to form a new list. So creates a new list with value prepended to the given list. So again, it creates a brand new list. So here's an example. So if I have the value 1 and I cons that with 2, 3, then what's going to happen is Haskell's going to create, or the function's going to create a new list where 1 is the first element, 2 is the second element, and 3 is the third element. So this is going to be 1, 2, 3. Okay. So another thing I can do is I can chain together cons operators. So for example, I can actually create the same list, 1, 2, 3, by taking 1, the value 1, and then doing cons, and then taking the value 2, and then doing cons, and taking the value 3, and doing cons with the empty list. So this, if I type this into the interpreter, it's going to return the list 1, 2, 3. Okay. So I have a question for you. Is cons left or right associative? Is cons left or right associative?
Looks like it's right. Starts the right,
Probably
moves
right,
left.
would be my guess. Because you need to see the list is there for you to know that you can do that.
Right, exactly. So let's, so it's right associative. It has to be right associative. And exactly for that reason, Tristan. So, so if I have this again, when I say it's right associative, or when we say this, that means that the parenthesization is going to be like that. Okay, so this is the only way it could be, because I have the way that we define cons is it takes an item and then it takes a list. It takes a value and a list and then creates a new list. So what happens on the right-hand side of the colon has to be a list. Okay, so what this is going to do is create the list with the value 3, and then that maintains this notion that we have a list to cons with. Whereas if I did if the parenthesization was like this, left associative, this is a type error. Why is that a type error?
Because the right side of the colon is not a list.
Exactly. Good. So the value 2, that's not a list. That's a number. And I can't cons a value with a number. Okay, so it has to be right associative. So again, if we come back to the correct right associative version, so this whole thing is going to result in a list 2, 3. Okay, and then this whole thing becomes the list 1, 2, 3. Okay, any questions about cons? So I expect everybody to memorize cons. You're going to be using cons a ton. So you have got to be, you have to understand what cons is and how to use it, how it works. Cons is a fundamental operation in Haskell for working with lists. And we'll talk more about cons as we go. Okay, so the next function that we're going to talk about, or we're going to start talking about some named functions. So the first one is called head, and in functional languages or Lisp, this is also called car, kind of from the olden days. And the basic idea is if I head takes a list and returns the first element in the list. Okay, so I can call head on a list. So what's going to be returned here?
4.
The value 4. Okay, good, because 4 is the first element in the list. Okay, what about this? The head of the empty list. What's going to be returned?
An error.
Empty or error?
Right, nothing's going to be returned because this is an error. And what kind of error is this? Is this a runtime error or is this a type error? Any guesses?
Runtime.
I would imagine it's runtime since there's nothing to have a type in there.
Runtime.
There's a runtime error.
Look at us being smart.
We're just being
In
smart
fact,
and not
the
saying
way
anything
that
to the class.
head is defined
Yeah.
in Haskell, this is actually, if we try to call head on an empty list, this throws an exception in the head function, and so because they're not catching the exception, this turns into a runtime error, which is basically an exception. Okay, any questions about head, the head function? Okay, there's like a reciprocal to head, which is called tail. Sometimes this is called cdr, like in Lisp,
Cooter.
old-fashioned. And so the basic idea of tail is that it returns the list that you give it minus the head. So it gives you everything back from the list but the head. And again, it returns a new list just with the minus the head. So if I give it the list I had before, okay, what's the tail of this list?